I hope that you guys are staying safe and productive at home or wherever the virus has taken you. Today, we're going to be talking about how to calculate the pH of a strong acid or strong base. And let me go ahead and get my pen going. All right, it looks like we're good. All right, so first of all, remember that a strong acid is one that completely disassociates into ions when it is placed in solution. That means that the concentration of your hydrogen ions, oops, the pen is not working, hold on a second. All right, that means that the concentration of the hydrogen ions is going to be equal to the concentration of the original acid. So for example, if I tell you that you have a 0.1 molar solution of HCl, what that really means is that all of it has dissociated, and in fact what you have is 0 of that HCl because all of it has separated into hydrogen ions and chloride ions. And because of that, the concentration of the hydrogen ions is equal to the concentration of the original acid, which was 0.1 molar. Just to remind you, these are the 7 strong acids that you need to know, and you need to know them by name and by formula. All right, let's go ahead and do an example. So what is the pH of a solution that is labeled 1.0 times 10 to the minus 4 molar nitric acid? What is the pOH of that solution as well? All right, so to begin with, we remember that pH can be calculated by taking the negative log of the hydrogen ion concentration, of the H plus concentration, which in this case, that's going to be negative log of 1.0 times 10 to the minus 4, and that gives us a pH of 4.00. Remember, in terms of the significant figures, if we started with 2 significant figures for the concentration, we end up with 2 decimal places for our pH. From there, now we need to calculate the second part, which is going to be the pOH. And we can do that in 2 ways. Well, one of the ways is going to be to utilize the equation that says that the pH plus the pOH is equal to 14. And so from there, we can solve for the pOH directly. This is going to be the easiest way. So we're going to go ahead and say that the pOH is equal to the negative, is equal to 14 minus the pH. And of course, that's going to be 14 minus 4.00, and therefore our pOH is going to be 10.00. That is it. We are done. All right. The second way would have been too complicated, so I'm actually not going to go over that too much. But if you wanted to, basically what you could do would be to take the hydrogen ion concentration and utilize the Kw equation to solve for the hydroxide ion concentration. So I am going to go over it. The hydroxide ion concentration would have been Kw over the hydrogen ion concentration. Once you had your hydroxide ion concentration, then you could find the pOH by taking the negative log of the hydroxide ion concentration. I encourage you guys to try this other method and see if you get the same answer, right? So method number 1 is here, and we got to our answer. Method number 2 is right here. All right, now, strong bases, remember that these are going to be the ones that completely dissociate in solution to provide hydroxide ions. These strong bases included the group 1 metal hydroxides and the heavy group 2 metal hydroxides starting from calcium hydroxide. Remember that you have a list of these strong bases at the beginning of the chapter. Now, the hydroxide concentration that comes from these bases can be easily calculated. So for example, for a group 1 metal hydroxide, the concentration of the hydroxide ions is equal to the concentration of the original base. So for example, if I had a 0.1 molar sodium hydroxide solution, that sodium hydroxide would completely dissociate to provide us 0.1 molar of the hydroxide ion concentration, right? So basically, the hydroxide ion concentration is equal to the concentration of the base for a group 1 metal hydroxide. That's important, group 1 metal hydroxide. On the other hand, if you have a group 2 metal hydroxide, things are going to be slightly different, because for every molecule of calcium hydroxide, you actually have 2 hydroxide ions. So if you started with a 0.1 molar solution of calcium hydroxide, then you in fact have twice that concentration of hydroxide ions, right? That's going to get multiplied by 2 to give you 0.2 molar. Again, because of the fact that every one of these molecules of the base is going to have 2 hydroxide ions, right? So this is going to be important. Once you have the hydroxide ion concentration, then you can go ahead and calculate the POH by taking the negative log of the hydroxide concentration for either case. All right, let's gonna go ahead and do this example. So find the pH of a 0.25 molar solution of barium hydroxide. Of course, barium hydroxide is a group 2 metal hydroxide, which means that its formula is BaOH2. This is a strong base and it would completely dissociate into the ions, barium ion, barium 2+, and the hydroxide ion, which is -1 charge. But notice that because of the formula, I need to balance this by utilizing a coefficient of 2, which indicates that every one molecule of barium hydroxide provides or separates into 2 hydroxide ions. Since we said that this was a 0.25 molar solution, in reality what we have for the hydroxide ion is a concentration of 0.50 molar. While for the barium we have 0.25 molar, although we don't need that. Remember that in reality you don't have any of the barium hydroxide because all of it has separated. Now that we have this hydroxide ion concentration, we can utilize that to find the pH, and we can do that in 2 ways. One of the ways would be to go ahead and find the POH first. Once we have the POH, then we can solve for the pH. That's my favorite way to do this. Basically, we're going to take the POH, or we're going to find the POH by taking the negative log of the hydroxide ion concentration, which in this case is the negative log of 0.50, and that gives us a value of 0.30. From there, we find the pH by utilizing the equation that says 14 minus my POH, which is going to be 14 minus 0.30, and that gives us a value of 13.70. That is our answer. Alternatively, you could have used the KW equation, so method number 2 would have been to take the hydroxide ion concentration and use the KW equation in order to find the hydrogen ion concentration. So H plus is going to be equal to KW divided by the hydroxide ion concentration, which we had. Once we solve for the hydrogen ion concentration, then we could utilize the equation that says that the pH is equal to the negative log of the hydrogen ion concentration. Again, I encourage you guys to try that method at home as well to make sure that you get the same answer. All right, the second example here is for sodium hydroxide, and I'm gonna let you guys try it at home. Sodium hydroxide is a group 1 metal hydroxide, so this one will be easier than the previous problem. And once you do this problem, you should find that the pH is going to be equal to 13.40, and let me know if you have any problems getting to the answer. The next example is, what is the concentration of a solution of potassium hydroxide that has a pH of 11.89? So in this case, we're kind of working backwards. We're starting with a pH, and we need to get eventually to the concentration of potassium hydroxide. So how do we go about this? Well, one of the ways to do this is that I know that from the pH, I can find the POH by using the equation that says pH plus POH is equal to 14. Once I get the POH, then I know that I can convert that into a concentration of hydroxide ions by utilizing the inverse log. And finally, once I have this, I need to know what is the relationship between the concentration of hydroxide and the concentration of the potassium hydroxide. Since this is a group 1 metal hydroxide that has only one hydroxide ion, then the concentration of potassium hydroxide is equal to the concentration of the hydroxide ions. So once we have this, we are done for this particular problem. Let's go ahead and get started. All right, so first of all, from the pH, I'm going to find the pOH. So my pOH is going to be equal to 14 minus 11.89, or really what I'm doing is 14 minus the pH. Let me go ahead and write that so you have your notes complete. Anyways, 14.00 minus 11.89, and that is equal to 2.11. From there, the next step is to find the hydroxide ion concentration, which we know that we can calculate by taking 10 to the minus pOH, and that's equal to 10 to the minus 2.11. Of course, once we do this in the calculator, we end up with 7.8 times 10 to the minus 3. Notice that we had two decimal places on the pH, or pOH in this case. That means that we are going to have two significant figures on the concentration. Finally, since we said that the concentration of the potassium hydroxide is equal to the concentration of the hydroxide ion, then basically we get our answer that the potassium hydroxide concentration is going to be equal to 7.8 times 10 to the minus 3, and that has molar units. That's it. Now, what if instead of having potassium hydroxide, I had asked you for the same problem, but with barium hydroxide? Well, you would have done the same first two steps, but at the end, once you had the hydroxide ion concentration, you needed to find what is the relationship between the hydroxide ion concentration and the potassium hydroxide, the barium hydroxide, let's say, concentration. So let's think about it. If we had something like barium hydroxide, which has two hydroxide ions, we know that that one separates into one barium ion and two hydroxide ions. So if we had the concentration of hydroxide ions as 7.8 times 10 to the negative 3, the concentration of the barium hydroxide base would have been half of that, because for every two hydroxides we have one barium hydroxide. So the concentration of our barium hydroxide would have been equal to 7.8 times 10 to the negative 3 divided by 2. And of course, our units are molar for any concentration.